Alright, so here are the second set of notes on radicals. This is on rationalizing a denominator. So the point of these notes is to really hammer home the point that we can't have square roots in the denominator. Alright, I want you to write over here that having, and it doesn't have to be a square root, having a radical in the denominator. Having a radical in the denominator is bad. This is bad. This is very bad. Big, big no-no. So, how do we get rid of it? That's the question. How do we get rid of these anomalies, and how do we divide radical expressions? That is the point of these notes. Now, first, we're not going to worry about getting rid of them just yet. We're going to worry about negative exponents, because this is how we're going to see them. So the first section of these notes is negative exponents. Negative exponents look like that. So we learned about rational exponents before. This time they might have a negative sign. Now, what does this mean? Well, yes, there is going to be a cube root because the denominator of the fraction is 3. So we are going to have an index of 3, but where is it going to be? It's going to be on the denominator of a fraction. So instead of it just being the cube root of x on top, it's going to be in the denominator of a fraction. Now, because there isn't anything else here, we're going to put a 1 here, because it's there is nothing else attached to this expression, so we have 1 over the cube root of x. Another way to think of it is like this. We have 1 over x to the positive 1/3. So if you remember from Algebra 1, negative exponents mean that you move whatever is in the numerator to the denominator. If the expression is in the numerator and it has a negative exponent, you move it to the denominator. And if the expression is in the denominator and it has a negative exponent, you move it to the numerator. Okay. So now, our next example is x to the negative 4/5. All right, this is equal to 1 over x to the positive 4/5, which, if we rewrite that in radical form, is going to give us 1 over the 5th root of x to the 4th. Or it could also give us 1 over the 5th root of x all raised to the 4th. We know from the last set of notes that these are equivalent, so this should not come as a surprise. Alright, now let's do the next example, which is 2x to the negative 3/7. And if I'm going too fast, feel free to pause the video. So keep in mind, in this particular expression, the only thing that's being raised to an exponent is the x. The 2 is not being raised to the negative 3/7. The 2 is separate. It's only the x that's being raised to the negative 3/7. So the 2 is not going to move, because the 2 is only being raised to effectively the first power. So on top, we're still going to have that 2. And on the bottom, we have the x to the positive 3/7 now. And now we can rewrite this as 2 over x to the 3/7 in radical form, which is the 7th root of x cubed. Or the 7th root of x, all of it, cubed. The 2 stays up top because it is not raised to the negative 3/7 power like the x is. If we were to have something, to have an expression where the coefficient on x is also raised to the same exponent, we would have to put it in parentheses like this next example. Now in this case, the 5 is also being raised to the negative 2/5. So here we only have 1 up here because everything is being moved to the denominator. And now we have 5x to the positive 2/5, which is going to give us 1 over the 5th root of 5 squared x squared. Which is the 5th root of 25x squared. Again, this is all in the denominator because our starting exponent was negative. So that should give you an idea of how negative exponents work. All right, now how to deal with them. So this is a technique called rationalizing the denominator. All right, so the first example that we have is 1 over the square root of 5. Now with square roots, there's a specific method that we should use because of this property that I should write right at the very top. If you have a square root of something and you multiply it by a square root of that same thing, you end up with whatever's underneath. And the reason why is because, and I'm actually going to write this out, the reason why is because the square root of 2 is 2 to the 1/2. And so we have 2 to the 1/2 times 2 to the 1/2. And when we multiply two expressions with the same base and different exponents, we add the exponents together. So 1/2 times 1/2, that gives us 2 to the 1st. Therefore, 1 over the square root of 5, 1 over the square root of 5, there we go, 1 over the square root of 5 can be written, or you can use this technique to rewrite this in a way such that the square root is not in the denominator. So there we go. So now we're going to rewrite it like this. And you might think, well, wait, I just wrote the same thing, but we're going to do something with it. So now we're going to multiply both the top and bottom of the fraction by something. Now, our goal is to get something that is not a square root on the denominator. So we're going to multiply, we're going to use this property right here, where we multiply the square root of something by the square root of that same thing to get what's underneath. We're going to use that same property and multiply both the top and bottom by the square root of 5 to give us our answer. So the square root of 5 times the square root of 5, on the bottom that's going to give me regular 5. Keep in mind that this doesn't just go away, it gives you what's underneath the radical. That's very important. That's a very easy mistake to make. When you do this property, it doesn't just go away, it doesn't just give you 1, it gives you what's underneath. And we're left with 1 times the square root of 5 on top, so that's the square root of 5. Okay. In general, this is actually a really important property to know. If you have 1 over the square root of something, then rationalizing it will give you the square root of that same thing over what was underneath the square root. So this property, like going from here to here, actually holds for every single real number. Actually, no. It holds for all positive numbers, if I remember correctly. Because with imaginaries, it gets wonky. So yeah, it works with all positive numbers. All right, anyway, x to the negative 1/2 is going to give us 1 over x to the 1/2, which is going to give us 1 over the square root of x, which means to rationalize the denominator, we have to multiply both the top and bottom by the square root of x. That way this will get rid of the square root, and we're left with what's underneath, which is x. And on the top we have 1 times square root of x, which is the square root of x. And again, this also follows the same property that we discovered up here. All right. So now, oh, one more thing. You might be thinking, wait, the square root of x, we have to put absolute value bars here. You are correct, we do. But at this point, when we're working with rationalizing the denominator in algebra 2, we're assuming that these are positive. When rationalizing the denominator in algebra 2 specifically, we're going to assume that these are positive. In pre-calculus, yeah, we would put absolute value bars here for sure. We would put absolute value bars here for sure. But in algebra 2, it's not that big of a deal. Oop. Here we go. Okay. The next one is 8x, all of it to the negative 1/3. This is going to give me, well, what goes on top? Well, there's nothing that goes on top because all of it is going to be moved to the denominator. All of it is being raised to a negative exponent. So we get 8x to the positive 1/3 on the bottom. This is going to give me 1 over the cube root of 8x. Okay. Now, this technique only works with square roots. As a matter of fact, if you're given this, if you're given a negative exponent and the denominator isn't 3, it is actually best to not write it in radical form yet. Instead, let's leave it in exponential form for a bit. We are trying to make the bottom, the denominator here, into something that has a power of 1, or an exponent of 1. So in order to do that, we're going to multiply this by 8x to some power, multiply the top and bottom by 8x to some power, but the power that we choose needs to make this denominator have a power of 1. And so in order to do that, we need to figure out 1/3 plus what is going to give me 1. Because remember, when we multiply these, we're going to add the exponents together. So this exponent here needs to be 2/3. The reason why this is 2/3 is because 1/3 plus 2/3 gives me 1. We have to figure out what exponent we would have to add in order to make it have a power of 1. So we're going to have 8x to the 2/3 here over, this is going to be 8x to the first. And so now, this is where we get, let's see. This is where we're going to have 8x, the cube root of 8x, all of it squared, over 8x. Now the cube root of 8 is 2, and x cannot be, x cannot, you can't take the cube root of just regular x, so we're going to leave it as the cube root of x. And all of this is going to be squared. And it's still over 8x. Now I'm going to come down here. And 2 squared is going to leave me with 4. And the cube root of x, all of it squared. We can rewrite it with the exponent underneath. And here we have a fraction that we can simplify. So this is going to leave me with 4 over 8 simplifies to 1 over 2. So that's going to give me the cube root of x squared over 2x. Because this simplifies to 1, and this simplifies to 2. Okay. Now we're done. Okay. We have a couple more. Actually, we have one more to do. And it is over here. It is negative 6 over the cube root of 9. Now, in order to rationalize this denominator, let's write this in exponential form first, because the index is 3. It's bigger than 2. So we've got negative 6 over 9 to the 1/3. Now, what power am I going to have to multiply by, or 9 to what power am I going to have to multiply by in order to rationalize this denominator? The exponent here is 1/3, so we're going to do 2/3. That way, when we add the exponents together, it gives me 1. And I'm left with negative 6 times the cube root of 9 squared over 9 to the first power. Okay, from here you can actually do this. This is going to be negative 6 times the cube root of 81 over 9. So this is going to give us, I want you to simplify the cube root of 81 real quick. So the cube root of 81 is going to be 3 cube roots of 3. Negative 6 times 3 is negative 18, so we should get negative 2 cube roots of 3 at the end of this, because negative 18 divided by 9 is negative 2. Again, this is negative 2 cube roots of 3. Negative 2 cube roots of 3. Whew, all right. We're going to move on to the next section. This is dividing rational expressions. All right. Dividing rational expressions. So when you're dividing rational expressions, you need to deal with the denominator first. So deal with the denominator first. So when you're dividing rational expressions, you need to deal with the denominator first. The first thing that you have to do is rationalize the denominator if you need to. For example, we have 7 over the square root of 2. So in order to rationalize the denominator, we need to multiply both the top and bottom by something. In this case, this is a square root, so this is easy. We can do square root of 2 over square root of 2, and we end up with 7 square roots of 2 over 2. We can't simplify 7 over 2. We can't simplify the square root of 2. We're done. All right, the next one is 6 square roots of 5 over the square root of 3. All right, next one, this is the next one. We're going to multiply both the top and bottom by, again, we're just rationalizing the denominator. We're not even touching the numerator yet. So the denominator is the square root of 3, so we're going to multiply both the top and bottom by the square root of 3. Again, this trick only works with square roots. With cube roots or higher, we have to put it in exponential form first. And we're left with 6 times the square root of 5 times the square root of 3 over 3. This is going to give me 6 square roots of 15 over 3. We can't simplify the square root of 15. You can try. It'll break down into 2 prime numbers. But 6 over 3 is 2 over 1. So this is going to be 2 square roots of 15. All right, the last example that I'm going to put on here is the cube root of 20 over the cube root of 4. So because this is the cube root of 4, we're going to need to write this as the cube root of 20 and then 4 to the 1/3 so that we can rationalize it. This way we know what power to raise 4 to when we multiply it. So 1/3, and then what exponent would we have to add in order to make this 4 to the first? That would be 2/3. This would give me over 4, and the cube root of 20 times 4 squared. Again, that's just because 4 to the 2/3 is the cube root of 4 squared. All right, so now the cube root of, this is 20 times 4 squared over 4 will give us the cube root of 20 times 16 over 4. which is the cube root of 320 over 4. Again, this is 320 over 4. And then from there, we have to break this down. So I want everybody to take a minute, break down the cube root of 320 with what little space you have, pause the video, and then we'll write the final answer. So we should have two groups of 3s. Oof. We should have two groups of 2s, right? Two groups of 2s, so that's going to be 4 on the outside, times the cube root of 5, and then these both cancel, so we're left with the cube root of 5. Okay. I'm exhausted. I'm probably going to do another take of this later. Work on the sample problems if this is the one that gets posted.